This launched rocket takes off at 60 meters per second at angle theta. It goes up to here where the velocity is only Vx, and then boom, it pops off again, and both pieces do this. So this explosion is going to give this some farther distance. So there's several things we have to do. We need to calculate this total distance downrange like that. And in order to do that, we'll need to get x to the maximum up there. And then once we've got that, we'll need to get y. And then it'll be like a two-dimensional motion problem. But we'll use, up here, we'll use momentum. So we're going to be doing basically like a 2D problem on this side. Then in the middle, we'll do a momentum calculation. And then at the end, we'll do another 2D problem. And let's say this is going to be in yellow, that's going to be in white, and this is going to be in green. So I'll separate all of these calculations. All right, if I have no idea what I'm doing, I still follow certain basic things. Number one, I crack the 60 meters per second at 37 degrees. I'm going to crack that right away. This is going to be 60 cos 37. This is going to be 60 sine 37. 60. This comes out to be 47. I'm just going to say 48, just to make my life super easy. And this one is like 36. Now you'll notice that's a 3, 4, 5 triangle as well. 3, 4, 5. 3 times 12 is 36. 4 times 12 is 48, and 5 times 12 is 60. So again, they're trying to help us out here a little bit. So our initial velocity vertically is 36 meters per second, and our horizontal velocity is 48 meters per second, which means Vx up here is 48 meters per second. That'll come into play when we do our conservation momentum at the top. So now we need to find x to the max spot and y at that height. The easiest way that I can think of to do this is to use y first, because I know that Vy final at the top is 0. So I know Vy initial is 36 meters per second, and I know the acceleration is negative 10 meters per second squared. So that allows me to find y. Y is going to be Vf squared minus V0 squared all over 2a. If I plug that in, I get 36 squared divided by 20, which is 64.8 meters. So we know our height is at 64.8 meters. I can also use the same thing, and I'll now just using a different equation to get time. The equation that I'll use is Vf equals V0 plus AT. So that's going to give me T is Vf minus V0 all over A. Remember, A again is negative 10. This was negative, or sorry, this was a negative over a negative, so that worked out. Again, V final 0, so this is going to be, once again, a negative or a negative. It's going to give me 3.6 seconds. So we know that it's 3.6 seconds to the top, so then I can multiply 3.6 seconds times 48 meters per second, because I can take x is equal to Vxt, and that's going to give me 173 meters. So this is 173 meters, and y is 64.8 meters. Okay, so we've got our launch point for the second part of the problem. So if we go ahead and now do the second part of our problem in white, we're in the momentum phase. Now it's Pi equals Pf. Let's take a quick review here. What we have is a rocket that has a velocity of 48 meters per second in the positive x direction. Now, there is an kind of an explosion or something, and then this becomes a momentum problem. They tell us that after the explosion, part B of the rocket we know that this is V total beforehand. We know that VB final is equal to negative 20 meters per second. Okay, so all we need is VA final, right? That's what we need from this. And we can do that by saying this is going to be MA plus MB times V total. We know that. It's going to be MA VA final plus MB VB final. Okay. Again, we're looking for VA final, so we're going to say VA final is equal to MA plus MB V total minus MB VB final all over MA. And we know all of that information from the previous section. Now we just do the math. MA, so MA plus MB is 2 kilograms times 48 meters per second minus MB, which is 0.5 times negative 20. And then we're going to divide that by MA, which is 1.5. And that gives me a 70.7 meters per second velocity for mass A. This shouldn't be too shocking because think about what's happening. If this rocket goes up to the top and then it explodes and throws the front forward, the back backward, doesn't it make sense that by conservation of momentum, whatever throw backward it gets, you're adding to that backward speed, that explosion is going to throw the front forward as well. And that's why this speed increases above 48. Okay, now it's not, you can't just add the 20 to this because it's a matter of mass ratios and weight ratios. All right, now we're ready for part 3. And we know that our rocket is 64.8 meters in the air. So it's 64.8 meters high. So it's kind of like a cliff problem. And it has an initial velocity of 70.7 meters per second. So the question is, what is x? Well, once again, we go back to our two-dimensional motion problem questions. We say x is vxt and y is vyt plus 1/2 at squared. Now, of course, y has no vertical velocity. So we say t is the square root of 2y over g. And then we're going to multiply that by our 70.7 to get our distance. So we're going to take 70.7 times the square root of 2 times 64.8 divided by 10. And that gives us an x distance of 255, good Dre Vance, bad writing, meters, 255 meters. Now we have to go back over here, and now we realize this is 255 meters. The question was asking how far are you away from, how far did it land from the original launch point? So we're going to take the 173 meters plus the 255 meters to get our 427 meters total, and thus our